But welcome everybody to our third session of the DigiFI African Scholars webinar. So this is a 4-part series that we've put together as part of kind of a training effort for African scholars. So far we've had 2 sessions. So the first one, Jessica Goldberg took us through thinking about your research question and what evaluations are, as well as giving us some context to what her fingerprinting study is. We've also had Dan Levy taking us through some of the why randomized components. And now we are very excited to have Patrizio Piraino taking us through sample size and power. Yeah, I think I'm going to hand it over to Patrizio. So he is a professor from the University of Notre Dame. He really specializes in labor economics and is one of our JPAL affiliates. And yeah, I think I'm going to just hand over to him.
Well, welcome everyone. Thanks for joining the session. It's nice to talk to people far away. I am going to share my slides and probably also, I don't know how the camera works, I may take the camera out. I will not handle the chat, so Amy will sort of mediate all the questions you have, and if I will stop every now and then to ask if there is anything that's worth repeating. If what I'm doing is correct, now you should have the slides in front of you. And this is what we're going to talk about today. Okay, let me put this here. All right, so you've seen a few in the previous webinars. You've talked about randomized controlled trials, what they are, why they're good, how they help us identify the causal effect of a policy or an intervention we're interested in. Today is a lecture that will help you understand and perhaps become a little more familiar with the details of how to decide, how to choose the right sample size for your evaluation. In order to do that, we're going to have to talk quite a bit of statistics. And so whatever notes you have from your previous stats courses, it's something that you may combine after this lecture, because we're going to talk about significance levels, we're going to talk about distributions. So there's going to be a bit of statistics involved today. But the end goal is, I want to evaluate something. How big should my sample be? That's really what this lecture is about. All right. So let's start with the first part, which we're going to discuss the difference between the true effect of something and the treatment effect we estimate from an evaluation. All right. Say that you're interested in the effect of policy A or intervention A on outcome Y, and the true effect that you don't observe because you haven't run your evaluation yet, the true effect of that intervention is here in the middle of this little target. So what happens is that we rarely see the true effect. What we do, we run an experiment and we get an estimate. Say we run 2 experiments of the same intervention with 2 different samples. Chances are we're going to get 2 different estimates, which are these 2 points here. The reason why we don't have the true treatment effect is because we generally don't see everyone. We generally don't have a fully controlled environment for everyone who was affected by the intervention. Generally, we evaluate the intervention using a sample. And because of chance variation in the sampling process, we're going to get different estimates every time we use a different sample. Okay? So it's important to understand the difference between the true effect, which we will never know for sure, and the estimated effect, which is what we get from our evaluation. Okay, so that's how we start talking about sampling. We need to understand the difference between the effect of the intervention, and so the treatment effect we're after, and the estimated effect we get from our experimental sample. Usually the way we estimate this is by taking the difference in the treatment group, the outcome we're interested in, minus the average in the control group, and that's going to give us the estimated effect we're after. Now, if it's true that every time I run an experiment, I'm going to get an estimate which is not necessarily equal to the true estimate, how do we deal with this variability? And that's what the lecture today is about. How do we deal with the variability in the experimental estimates? As I said, usually what we do, we take the average outcome in the treatment group, as you've seen in the previous webinars. We compare it to the average outcome in the control group, and that will give us the estimated effect. Usually we call it beta hat. Why do we put a hat on the beta? To differentiate it from the beta without the hat, which is the true effect. So the hat, as you will remember from your statistics class, is the estimate of the true effect. So when we put a hat, we're talking about an estimate. When we don't have the hat, we're talking about the true effect. So once we run our evaluation, we're going to get a beta hat, which is an estimate, and we want to know how confident we are that this estimate here, this beta hat, is close enough to the true effect. Okay? Now, what determines this confidence, how confident we can be? Well, as you've seen before, what randomization does, randomization creates a treatment group and a comparison group. And the reason why we randomize, as you heard before, is to make sure that the treatment and the control group are not systematically different by design. So randomization essentially eliminates any selection bias that there may be between treatment and control group. However, when we work with samples, there may still be some difference between the treatment and the control group due to the fact that we're sampling them from a population, and by chance, this sampling here that gives us the comparison group may result in a certain mix of people, and this sampling here that gives us the treatment group may result in a different set of people. So even though we have tossed a coin, and so the coin decides who goes here and who goes there, by chance, just because we're working with small numbers, by chance we may end up with this group being a little different than that group. And that's just because in a population that has a certain mix of characteristics, if you only take, in this example, for instance, if you only take 3 people out of this group and 3 people out of this group as well, then by chance you may get that the 3 people here look a little different than the 3 people here, just because we're taking only 3 people. So there is always a chance that these 2 groups are going to be different. So even though we're randomizing, the very nature of using small samples is going to put us at risk of some difference between the treatment and control group. And this is a chance difference, a difference that derives from sampling. So that's why the size of the sample is important, to minimize this risk, and we'll see why, okay? Because there's going to be some chance difference between these 2 groups, it is possible that our estimated treatment effect will differ from the true treatment effect depending on which samples we got in that particular experiment. So if we ran the experiment several times, it is possible that we would get different treatment effect estimates, simply due to the fact that every time we run the sample, we get a different control group and a different treatment group that will differ again by chance. I'll repeat this in a second. So please ask a question now if essentially all I've said so far is that there is a difference between the estimated effect and the true effect, and this difference comes from the fact that we're using samples. If this is not clear, please ask a question now. All right, I don't hear anything. Okay, good. So now that we understand that there is an estimated effect and that there is a true effect, how do we deal with this variability? Okay, imagine you run one experiment. Again, you're interested in the effect of intervention A on outcome Y. You run the experiment and you get this little X here is the one estimate you get after you run the experiment. And here it essentially says that the difference between treatment and control group is about 4. You can imagine any unit of measurement here. So $4, 4 rands, for cognitive test scores, whatever it is, okay? Now, say that now we run 3 experiments on the same intervention, on the same outcome. Because we're using 3 different samples, we're going to get 3 different estimates. So in these examples, for instance, 2 of them happen to be similar, but one is a little different. Now, this one estimate here is actually below 4. Now, let's say we run 6 experiments. Because we're using 6 different samples, and because there's going to be some random variation, some chance variation in the samples we're going to work with, now we're going to get 6 estimates. So now you see that we have some estimates that are a little higher, some estimates that are a little lower. Now let's say we run many experiments. Again, we're going to get even more estimates here. Even more experiments, more estimates. Remember, we're running the same experiment, same intervention, same outcome. What we're changing is the sample. But because we're changing sample, chance variation will result in different estimates. So if we run many more experiments on the same policy, we start having what you will recall, it's called a distribution of estimates. So we have, this is the frequency, so we have a bunch of estimates here between 4 and 5. Then we have some estimates below 4 and some estimates that are higher than 4. Higher than 6 is not very common, and lower than 3 is not very common. This is what the distribution looks like, okay? So now we have a distribution of estimates, and we can use statistical theory to tell us how this distribution behaves. And because we have randomized, we know that this distribution behaves normally, meaning that this distribution is going to be centered around the true effect, and it's going to have a normal distribution. So this is just the fancy version of this. So this is what the distribution looks like, which is essentially running the same experiment many times. So I get a lot of estimates. And this is exactly the same thing, but now we're going back to our statistics textbooks. But it's exactly the same story, okay? So what we know, because we have randomized and because we have studied statistics, we know that all these potential estimates I get if I ran the experiments many, many times, all these estimates, they're going to be centered around the true effect, the true beta. You see here, the beta doesn't have the hat. And all these estimates are going to be distributed like this. So now we can use this. We know that if we ran the experiments many times, we could get all these estimates. But most of the estimates we would get will be around the true value. So that's what we know. So we're going to use this information to figure out a way to say, how sure are we that we are around the true value? How sure are we that the estimate we got is not, in a sense, an outlier? It's not something that it's here or here, but it's somewhere around the true value. And the answer to this question will depend on our sample size and on a number of other ingredients that we're going to discuss today, okay? So say that you have, 2 small samples, as we saw earlier, and you have a treatment group and a comparison group or control group. If the sample is small, the chance that the treatment and the control group will be different is higher, because it is easier to get essentially people who are peculiar in a sense to get selected in a small sample. So you're essentially, we're not giving enough room to the sample to be diverse enough. So because we only, in this case, for instance, we're only taking 3 people. So it's more likely than these 2 small sample we're going to get are going to be different from each other. So if we're only taking 3 people from this pot and we're putting them here, and we're only taking 3 people from this pot and we're putting them here, chances are that these 2 samples are can be quite different from each other. If we take more people from the same pot, then we're allowing chance to have less of a role in determining differences. So now we have more people here, so it is more likely that these guys are going to be more similar to these guys. Why? Because we know that when we take a larger sample from an underlying population, the distribution, the true population parameters we're interested in is going to be closer to the truth in a larger sample. So essentially, this group of people here is more likely to be representative of this pot than this group of people which only has 3 people. Imagine you want to have a representative sample of Kenya, and you take a random sample of 5 people. It is very likely that those 5 people you interview are not going to be representative of Kenya, because there's only 5 of them. So maybe they're going to be more educated than the average in the real population. Maybe they're going to be less educated than the average in the treated population. But if you sample 5,000 people, then you're more likely to get an average, a representative sample of your population. So it's the same here. If we take more people, it is more likely that our comparison and treatment group are going to be more representative of our pot here. So essentially, there is less chance that these 2 groups are going to be different from each other. Okay? So by increasing the samples, we're giving chance a harder time to create differences, because we're making our comparison and treatment groups more likely to be representative of our initial pot here. And by doing that, they're also less likely to be different from each other. Any questions on this? Okay, I don't hear any virtual or physical hands. So, so by increasing the sample size, we're more confident that the treatment and comparison group will be similar to each other. Okay? What happens to our distribution we saw earlier when that's the case? Well, if you remember from statistics, what we do when we make something less prone to variability, we are making the estimates, we're making the distribution more centered, which means that if we get a larger sample size, we're gonna have less variability in the potential estimates. Now the estimates are more likely to be between 4 and 5. Before, there were a bunch of estimates here below 4 and a bunch of estimates above 5. Now we are more likely to get estimates that are between 4 and 5. So essentially, by decreasing the chance variability between treatment and control group, we have decreased the probability of getting from one single experiment estimates that are further away from the true value. Okay, so essentially we have reduced the variability of the distribution of estimates. I heard some, okay, I'll keep going. There was a bit of noise. So by doing that, we now have a distribution of estimates that is more centered around the true value. And that's going to help us when we try to figure out whether the estimate we get from a single experiment, if we're confident or not that that estimate is a true effect or not. So having a bigger sample means that we're less likely to observe a treatment and control group that are different from each other by chance. When that's the case, if we were to run the sample many times, with a bigger sample, we would get a distribution of estimates that is more centered around the true value. So that's the second important concept of today. First important concept, there is a difference between true estimates, true effects and estimated effects. Second important concept, the estimated effect changes every time that we run an experiment, but when we have a bigger sample, it changes less. Okay, so those are the two things we said so far. What about what happens for different types of population? So now we're moving to a second ingredient here. Say that you have a certain population and you have an outcome you're interested in. If that outcome is highly, there's a lot of variation in that outcome in your population of interest, then it's possible that you're going to get very different people in the treatment and control group. Okay, simply because there is a lot of different type of people here. So if I'm only getting 3 people, I'm going to get, you know, here I have a yellow person, here I have a red person, and so the only overlap is the blue little people here. So the point is that by having a very high variability in the outcome, I am more likely to get a difference in the two, to have chance differences between treatment and control group. Instead, if there is only, for instance, 2 types of participants in the population of interest, then I'm more likely to get the treatment and control group that are similar to each other. So this is the same story, right? I'm trying to figure out when am I likely to get some chance difference between treatment and control group. For a given sample size, so we discussed that the bigger sample size is going to reduce that chance. What about, given a certain sample size, is there anything else that determines a chance difference between treatment and control? And we're introducing what this might be. Well, one thing that for a given sample size determines a higher chance of a difference between treatment and control group is high initial variability in the population of interest. So if the outcome that we're interested in is highly variable in our population of interest, then for a given sample size, I'm going to have a higher chance of the treatment and control group being different from each other. If in the initial population of interest, there is less variability to start with, for the same sample size, I have less chance of getting a difference between treatment and control group. Okay, so concept number 3, given a certain sample size, if my outcome of interest doesn't have much variation in the population of interest, then I am less likely to get a chance difference between treatment and control group. So essentially, low outcome variation in the population of interest has the same effect as a bigger sample size. They both decrease the chance variability between treatment and control group. So this is concept number 3, high outcome variation in the population increases the chance of getting a treatment and control group that are different from each other for any given sample size. Okay? There is another one which also gives you, affects the potential of chance differences between treatment and control group. And this is how even the split is between the treatment and the control group. say that our control group is much larger than our treatment group. And this could be the case, for instance, if the treatment is expensive. Say that you're running an evaluation on a treatment that is very hard to fund, or is just very difficult to do for logistics reasons. But maybe the control group is easier to have because it's cheaper, or it's just you have some other ways of getting control units which are easier to do. So you may end up, in many real case scenarios, you may end up with a control group that is larger than your treatment group. Now let's say that you have an extra unit and you want to decide whether to put it in the treatment group or in the control group. Well, intuitively, if you put it in the treatment group, because you're creating a bigger treatment group here, you're reducing the chance variation between treatment and control group. Why? Because we saw earlier that by having a bigger group, you're making that group more similar to the underlying population. So if I have this extra unit and I'm worried about these two groups not being representative of the underlying population, then I'm better off putting it here, because this group is more at risk of being different from the underlying population. So by putting the extra unit here, I'm making it more likely that this group is becoming more representative of the underlying population, because this group is already big enough, so this group has a lower chance already of being peculiar, of being different than the underlying population. So essentially all this to say that a more even split between treatment and control group in terms of size will reduce the chancing variability. So concept number 4, I think we're now. Concept number 4, if you have a treatment and control group of similar size, so the sample of control units and the sample of treatment units are of similar size, say 50-50%, then you are less likely to get a chance difference between the treatment and control group. Why? Because if you have a very small treatment group or a very small control group, then that group will be more likely to be different from the underlying population. So for a given number of participants, a more even split between treatment and control will give you more power, will give you less chances than there's going to be chance variation between treatment and control group. So far we saw 3 ingredients: sample size, outcome variation, and split between treatment and control groups. And those 3 ingredients, they all 3 of them, they affect the distribution of potential estimates. How do they do that? We saw it earlier. If treatment and control group are more representative of the underlying population, we saw earlier that the distribution becomes more centered around the true value. So if I have a higher sample size, this is what happens. If I have lower outcome variation, this is what happens. If I have a more even split, this is what happens. All 3 things we saw so far, they all have the same effect. They make our distribution of estimates more centered around the true effect. They all do the same thing for different reasons, but they all do the same things. So by doing that, we have this potential chance distance from the true effect is reduced. And that's what we want. We want to have an estimate from our experiment that is less likely to be driven by chance sampling variability. And the best way to do that is to make sure that the sampling distribution is as centered as possible, as close as possible to the true value. So in this case, it's further away. We are more likely to get values that are further away from the true value. Here we are less likely, because now most values are closer to the beta, the true effect. Okay? So sample size, outcome variation, and split between treatment and control group, they are all things that affect how likely we are to get estimates that are far away from the true effect when we only run one experiment. Okay? So, if we understand the difference between the true and the estimated treatment effect, and if we understand that each single experiment that gives us one estimate, and we have seen how likely we are to see that that estimate is far from the true effect, and that likelihood depends on these three components we just discussed, then we can move to the next level, which is, okay, now, what do you mean that you're confident that this estimate is going to be close to the true effect? What do you mean by that? And here we go back to our introductory statistics idea of hypothesis testing. Okay. Now I have to go fast on this because I want to spend more time on power, which is something that is less covered in introductory statistics. So I'm going to go a little quick on hypothesis testing, and I encourage you to go back to your stats textbooks to if you need to. Meaning probably most of you don't need to, but if you do, go back to your stats textbooks and for hypothesis testing.
Sorry, Patrizio, can I just jump in before you start with hypothesis testing? So there was a question on the chat on how one determines outcome variation.
Right.
So just to maybe clarify that before we.
Right. So we're gonna see that when we're here in the last point. But this is a good question. It's always good when people ask questions for slides that are about to come. So the way we do that is, let's say that you're, for instance, interested in the effect of an education intervention on students' test scores in a particular area of your country. Then what you would do, you would talk to the schools in that area and get an idea of what the existing distribution of scores is. So that's going to give you an estimate of how variable your outcome is in the population of interest. And when that's not possible, you're going to use a similar population in another area of the same country. And when that's not possible, you're going to use a similar outcome in a neighboring country. And when that's not possible, I guess you go to another continent. But in general, what you try to keep it as close as possible to your population of interest so that you can get an estimate of the variability of your outcome for the population of interest. Any other questions before I move to hypothesis testing? Okay, so that was a crucial one. Thanks for asking the question. Hypothesis testing. So we know that there are these ingredients, and we know that if we can run the experiments many times, we would get many different estimates. The thing is, we only run the experiment one, usually, so we only get one estimate. See, now the beta has a little hat on it. So this is our single estimate we get when running the experiment one time. So now we have this estimate, and we want to know how confident are we that this estimate is close to the true effect. So the way we go about it is, okay, let's first see if this estimate is, I can trust the fact that this estimate is different from 0. Okay, so that's the first thing we do. And remember, the way we do this in hypothesis testing is we specify a null hypothesis, which there is no effect. So our null hypothesis is that the true beta is actually 0. Okay? Again, I'm going to go quick here. So we start essentially by assuming that the program did not have any effect. And then we ask ourselves, if the program didn't have any effect, how likely am I to see this estimate from one sample? So this is a bit of a thought experiment. So remember what your statistics professors told you at some point in the past. This is how we think. If the true effect is 0, and now I have only one estimate which comes from my one sample, how likely is that I get this estimate if the true effect is 0? So how do we answer that question? Well, essentially what we say is, well, if it is very unlikely that I get this estimate under the hypothesis that the true effect is 0, then I feel confident rejecting the null hypothesis. Okay? Let me repeat this with a graph. So if I assume that the true effect is 0, then the distribution of potential estimates would look like this. If the true effect is 0, then if I ran the experiments many, many times, this is the distribution that I would get. The same distribution we saw before, but now it's centered around 0 because I am assuming that the true effect is 0. So if this is what the distribution of estimates looks like under the null hypothesis, then the fact that I get an estimate this big suggests that it's very unlikely that this is true, that this is the true effect. If I get this number instead, then this is more consistent with the null hypothesis. Okay, if the null hypothesis is true, this kind of estimates would happen many times. So I feel less confident in saying, hey, my estimate, I can reject the fact that this estimate is different from 0. I feel less confident because under null hypothesis, in a lot of situations, I will get this number. Not so much in this case. So essentially what I'm saying is, you know, when we say the estimate is statistically different from 0, what we say is essentially there is it is quite unlikely that the estimated effect is due to chance. That's what statistically different from 0 means. In this case, instead, when we say the estimate is statistically insignificant, what we're saying in plain English is there is a reasonable likelihood that the estimate I'm getting is actually due to chance, but the true value is actually 0. So statistically insignificantly means that I'm not confident that the number I got is actually different from 0 because there is a number of plausible scenarios under which I would get this number. When I say it's statistically different from 0, I'm saying it's quite implausible that I would get this large number if the true underlying value is 0. Okay, that's what just a refresher of what statistical significant means. Okay, unfortunately, I don't have time to go deeper into this. Another quick refresher: how likely? When we say likely, what is the number we want? So what we want, usually remember, is the 5% significance level, which means that I only want to take a risk that I say that something is different from 0, when actually 0, I only want to take a 5% risk of that. So essentially, by using a 5% significance level, 5% of the times, I will say that the program had an impact when in fact it didn't. So that's what, but in 95% of the cases, I will not do that. So in 95% of the cases, I will be confident that I'm rejecting something that is very likely to be close to 0, which that's why we call it confidence interval. Okay. So sorry for the very 10 minutes refresher of something that takes usually one semester at university, but that's what we have today. So
great.
Remember, yes.
Can I jump in just with a question, or do you want to finish wrapping up with this section?
Yeah, maybe let me just a quick refresher of what the cutoff values are, right? So remember, if we want to get a 5% confidence level, then what we do, we get these cutoff points, and we say if the estimate is above or below this cutoff points, this is for a two-tail test, as you will remember, then I will reject the null, and I will say beta hat, the estimate I get, is statistically different from 0, is significantly different from 0. Okay. If I get a number that is, if I get a number that it's on below my cutoff value, then I will reject it and say, sorry, my estimate is statistically insignificant. I don't feel confident enough that the number I got is different from 0. That's what we're saying. Yes.
Great. So there was just a question about why the 5% level is selected as the cutoff value and not 10% or 20%.
Sure. Like many things in research, at some point there is a convention that it's established on what is the acceptable level of risk we want to take. Here we're trying to minimize the risk that we say that something is positive when it's not, right? So then the convention usually is to use 3 significance levels, and the most common one is 5%, but sometimes we look for 1%. So essentially, I want to be 99% sure that I'm rejecting something when I'm not confident enough, and sometimes it's 10%, which means that I'm 90% sure. So I'm sorry, I don't have a fantastic answer to this. This is a convention that we took essentially by using these 3 different levels, and usually the one in the middle, so 1 and 10 are the typical bounds of the confidence that the significance levels that we operate with, and 5% is usually the one we use to say that something is statistically significant or not. So it's I would call it a convention, really. And it derives from the fact that 95% is a fairly big number to say, okay, I'm confident that I'm not making an error here. So if we go back to them to this, for instance, by setting a 5% significance level, I'm allowing myself to be wrong only 5% of the times. If I'm setting at 1% level, I'm allowing myself to be wrong only 1% of the time. So I'm giving myself a harder time to reject the null. If I set a 10% level, I'm allowing myself to be wrong 10% of times. So we have, the convention is to allowing ourselves to say that something has an impact when actually didn't, only 5% of the times. Okay? All right, so this was the quick refresher on statistical significance. Now let's move to power. Now, in order to talk about power, we need to remember what a type 2 error is. A type 2 error is the probability of concluding that something has a no effect when actually there is an effect. So in this little picture here, there's a pregnant woman. The type 2 error would be to tell the pregnant woman, you're not pregnant, because we can see that she actually is pregnant. So we want to avoid the risk of a false negative. We know if the truth is that there is an effect, we want to avoid the mistake of saying, no, there is no effect, right? So say that there is, again, let's go back to the educational example. Say you have an educational intervention and the truth is that the educational does help the children. You want to avoid the risk of saying, no, this intervention is useless. It doesn't help the children. If the truth is that it does help the children, you want to make sure that you detect that. And that's what the concept of power does. So statistical power is the probability of avoiding this type of mistake. Is the probability of avoiding to say that something doesn't have an effect when actually it does have an effect. So how does that work in the graph we were looking before? So the red or orange line here is the distribution of estimates under the null hypothesis that the true effect is 0. So this is the distribution effect. Remember, this was our critical value for significance that we saw earlier. Now, what if the true effect is beta? If the true effect is beta, this is the distribution of estimates. So this is an alternative hypothesis. This is the null hypothesis. The true effect is 0. So if that was true, this is what our estimates would look like if we ran the experiments many, many times. If this is the true hypothesis instead, this is what the distribution of estimates would look like if we ran the experiments many, many times. So now we have 2 potential alternative truths. Hypothesis 1, there is no effect. Hypothesis 2, the effect is beta. And those 2 hypotheses, they come with 2 potential distributions. We want to know how likely am I to say no, to say that something is statistically insignificant when this is true. And it's going to be this area here. Why? Because if this is the critical value at the 5% level, remember, every time we get an estimate, we would that it's below this value here, we will reject it. So every time our estimate is below this yellow line here, we will reject it because it's closer to the null hypothesis of 0. So that's why we will reject it. So let's say we conclude that the effect is statistically insignificant because our estimate is somewhere here. Under the alternative hypothesis that the true effect is beta, that would happen, in a certain percentage of cases in this alternative world. And these cases will be all this area here below the green or blue, whatever color this is, this green line here. Okay, so in all these cases, I'm giving myself a probability of rejecting an effect that is actually positive. Okay, let me rephrase it the other way around. Say the true effect is 0, and I'm using a 5% significance level. Sorry, say the true effect is beta, and I'm using a 5% significance level. Okay, because the distribution of estimates will be this line here, then whenever beta is above the yellow line, I will reject the null, and I will say that the estimate is statistically different from 0. And that happens if the true value is this beta here. That happens for all these values here. Okay, so this gives me the probability that we obtain a treatment effect that leads us to reject the null hypothesis of 0. So every time we get a value that is above the yellow line here, if the true value is beta, that's going to happen in all these cases. And so this area below the line here is our power, is the probability that we're going to get a correct positive, that we're going to say that something is positive when the true is indeed positive. And why is the power not 100%? Because there is some percentage of cases here on the left side where I will say no, even under the assumption that this was the real value. And why I will say no? Because I gave myself only 5% chances of rejecting the null, and so I put my critical value here. So maybe this was something you also covered in your statistics class. There is a trade-off between significance and power, right? Because by setting a higher significance level, you're moving the yellow line to the right, which decreases the power. Okay, so which balance do we want here, right? So say that the true value is beta, is this beta now. Okay, so this is the same graph, but now the actual true effect is less. You see that now I have less power because now the beta is closer to 0. So the two potential distribution, the H0 and the H beta here, are closer to each other. So now a bunch of the potential distribution here is actually on the left side of the critical value. Under the alternative hypothesis, the beta here is this one, the true beta is here. Because it's closer to 0, there is quite a bit of overlap between these two distributions. So now the yellow line is going to be much further to the right. So now the range of values under which I will reject the null is now covers much less of the area of the alternative hypothesis here. So now I have less power. I have less chances of saying, yes, this is different from 0 when actually it's true. So this introduces a very important concept, which is that if the true effect is smaller, that true effect is going to be closer to 0. And if it's closer to 0, the potential distribution under the null hypothesis and under the alternative hypothesis are going to be closer to each other, which means that the power to detect a true positive is going to be less in this case, simply because now this distribution has moved to the left. Okay? So the only thing that changed between here and here is that now the true effect is smaller. But otherwise, we're making exactly the same calculation, okay? So let me just repeat the two main concepts here. Concept number 1. Actually, let me start from here. We want to avoid, as much as possible, the probability of saying that something is statistically insignificant, so that something doesn't have an effect when actually there is an effect, okay? How do we avoid that? In order to make that calculation, we need to know that what the distribution of estimates would be if there was a true effect. Now, let's say that the true effect was this beta here. If that's the case, we are going to have a bunch of situations in which our estimated effect will fall under this area. But if the true effect is smaller, I'm going to have less space, so to say, under which I can say that, okay? Simply because now the null hypothesis and the alternative hypothesis are closer to each other. Distributions are closer to each other. So I have less power. So the effect size is very important when it comes to power, okay? And really the intuition here is that because we set this critical value here to the right of 0, if the true effect is closer to 0, then this distribution is moving more to the left of the critical value. This is what's happening. If the true effect is larger, then this distribution is largely on the right side of the critical value. So the larger the effect, the more distribution I have, the more alternative distribution I have to the right side of the critical value. So the more likely I am to accept a true positive. The smaller the effect, the less likely I am to accept a true positive, because this smaller effect overlaps a lot with my alternative hypothesis, which is 0, okay? With the null hypothesis, which is 0. So the power of your test will also depend on the size of the true effect. The bigger the true treatment effect, the easier for you will be to be on the right side of this yellow line, the higher your power to detect a true positive effect, okay? Any questions on this? Okay, I'm going to move in the meantime, and because we're going to talk about the ingredients anyway again. So, what are the main ingredients of your power? Well, we saw that the effect size is an important ingredient. So, essentially, if the true estimated effect is bigger, then I'm more likely to avoid a type 2 error. Okay, so that's one ingredient. We saw earlier that greater variability in the outcome variable makes it harder to distinguish an effect. We saw that a larger sample make it easier to distinguish an effect. And we saw that a more even sample split also makes it easier to distinguish an effect. So we saw these three effects earlier, and we saw the effect size just now, okay? So those are the 4 main ingredients. Now, we said, okay, here we can get an estimate of the variance by looking at similar outcomes or by looking at prior outcomes. Sample size we can control. Sample split we can control. So these three ingredients, we can get a number. But we don't know what the true effect is. That's why we're doing the experiment in the first place. So now we have something here that we don't know. We don't know if the true effect is out here or if the true effect is closer to the zero. And that's going to determine our power, because if it's further away, we just said that we are more likely to avoid a type 2 error, right? So how do we go about something when we have 4 ingredients, but we are missing one, okay? And that's where we get to something called the minimal detectable effect, which we are going to call MDE. So the MDE is the minimal effect, the size of the minimal effect that can be detected for a given power, for a given significance level, and for a given sample size. So we've seen that a larger effect means greater power to detect it, because we're further to the right, so we have more area under the alternative hypothesis under which we're going to say, yes, this is positive, okay? But we don't know how much to the right the true effect is. But in order to calculate how much sample size we want, we need to think about what this effect might be, because we need that ingredient in our calculation. So we're going to ask ourselves, how large must the effect beta be so that we can detect it with 80% power and this sample size n and 5% significance? So the answer to that question is essentially going to give us the final ingredient to the power calculation, okay? So going back to the graph, we're saying, okay, this is our null hypothesis, this is our zero, this is our critical value, okay? We said, I want to be conservative, so I'm going to give myself a 5% significance level, which means I want to reject the null 95% of the time, okay? So then in order for me to be confident about the in order for me to know how much sample size I need to balance these two needs that I have. One is that I want to be conservative on the significance level side, and one is that I want to allow myself to detect a true positive effect on the power side of things, okay? So how far to the right I need to be in order for me to get the power that I need? How far to the right does this distribution need to be to get this area to a number that I am okay with? Usually the number we use is 80%. So we want to be sure that 80% of the times, if there is a true effect, we're going to reject the null hypothesis and say that that coefficient is statistically different from zero, okay? So in order to get that 80%, we need the true effect to be far out enough so that the potential distribution associated to that effect is going to be to the right of the null hypothesis enough to give me 80% of the chances of being essentially to the right of this yellow line, okay? So we're asking ourselves, if I want this area to be 80%, and I want the area between the yellow lines to be 95%, given these two ingredients, and given a certain sample size, which determines how spread out these distributions are, given these parameters, how big must the true beta be for me to get 80% of area below this distribution here? So that's what we're doing. And so we need to set this we need to understand what this minimal detectable effect size is. Okay. Any questions on this? Great. Now, there is a lot of ingredients here, and even myself, sometimes I mix up words, significance, power, but it's important to repeat one more time, okay? Power is about avoiding a type 2 error, right? Let's go back to it. Which is that we want to, when we say we want to increase power, we want to increase the probability of detecting a positive effect when the true effect is actually positive. So we want to increase our power to say, yes, there was an effect if the underlying effect was indeed true. That's what we're trying to do, okay? Since we have the critical value coming from the significance level we discussed earlier, then that power is going to depend on how far to the right the distribution of the potential of the true effect is, the potential distribution of the true effect is. So for a given sample size, which determines essentially how spread out this distribution is, for a given significance level, which determines where the yellow line is, and for a given power amount, which determines how much area I want to have under the distribution here to the right of the yellow line. For these three parameters, if we set these three parameters, the minimal detectable effect tells us the smallest, so the threshold essentially to the right of 0, above which I'm getting 80% of or more power. Anything below that threshold gives me less than 80% power. So anything below this beta here is going to move this distribution a little to the left, which is going to decrease this area here. So I'm going to have less than 80% power. If the true effect was bigger than this beta here, then I'm going to have even more power because this area would increase. Okay? So I don't know if we have time to go into cluster designs, actually. Probably not. Let me just move to the practice of it. So let me conclude with that. In practice, how do you go about it? First, you set the desired power. Usually we do 80%, and you set your significance level. Usually we do 5%. Then you decide on a sample split. I want to have 50% of the units in the treatment group and 50% on the control group, for instance. Then you ask yourself, what is a plausible treatment effect that I can expect from this type of intervention? You know, based on the literature, based on my experience in the field, based on what Nobel Prizes say, what is that I think a reasonable effect size of this intervention could be? And you can use that to set your MDE, okay? On the basis of that, then you estimate the variance, and this other thing we haven't had time to cover, so let's just stick it to the variance. Then you estimate the outcome variance. As we said, you can do it by using another sample or prior studies. Now you have your 4 ingredients, and you can estimate your sample size. You can do your power calculation. Now, luckily, there are different resources that do the calculation for you, but it's important that you understand what the ingredients are, okay? And these are the resources that I was talking about. So I'm sure that Amy will share the slides with you. Yeah, I think I'm done. Or maybe Amy wants to talk about this.
Yeah, so I mean, I think, so I've just popped on the feedback form for folks to fill out very quick feedback just on the session. We have just a couple of questions that came through the chat that I wanted to flag. And if there are any very burning questions, you can pop them in the chat. Otherwise, send me an email and we'll connect you with the resources to answer your question. So the one question was just about, so there was one question, Blaise, I didn't really understand your question, but I'm going to ask it and we can see if we can understand what you're asking about. So he asks how many estimators we can apply a hypothesis test to at the same time. I'm not sure exactly what you're asking, but just putting it out there. And his follow-up is about the degrees of freedom and what you're looking about for degrees of freedom.
Okay. Okay, the first question I'm not sure I understand. So usually the degrees of freedom is a good question. Let me answer in a different way. So remember, the degrees of freedom has to do with how many parameters you have in your regressions, right? So I'm going to say I'm going to sort of bypass your question and say something related, which is because I don't want to go into degrees of freedom in sort of stats courses. But let me tell you one thing that it is relevant for power, which is when you add more covariates to your evaluation. Say you run the experiment and you have a treatment and control group, and then you run a regression where your treatment variable is your treatment dummy is going to give you that beta coefficient. You probably saw this in the other webinars, I'm not sure. But essentially, if you do that estimation, it is good to include some other controls in your regression. Why? Because you're essentially reducing the residual variance, which gives you more power. So I'm just going to state, I don't want to, because that's another lecture altogether. So I'm just going to say that, and that's kind of related to degrees of freedom in a way. Okay. So sorry for being a bit slick about this.
That's great. Cool. I think those were the main questions that came through on the chat that weren't answered kind of as we went. But yeah, just a reminder for everybody to fill in the feedback form. I've popped it in the chat. And then our next session is on the 29th of June, where Emily and Gabe will take us through kind of thinking about how to write a successful funding proposal and kind of tips and tricks around that. Any final words from Nidhi or Patrizio before we close?
No, thanks so much for listening to this. And if you have any questions through Amy, please feel free to ask.
Great. Thanks so much, everybody. And thank you so much, Patrizio, for presenting all this. I know it's a lot of energy and a lot of work. So thank you very much to you.
Thank you.
Cool. Cheers,
Thanks,
everybody.
Prof.
Bye-bye.
Bye.
Bye.
Thank you. Bye.